please join me in extending the warmest possible Seattle welcome to Professor Stephen Hawking.
Can you hear me? In this talk, I want to describe an exciting development that may transform our view of the universe and of reality itself, whatever that may be. The idea is that we may live on a brane or surface in a larger space. The word Brane, spelled B-R-A-N-E, was introduced by my colleague, Paul Townsend, to indicate a generalization of a membrane to more dimensions. I suspect the pun on Brane was quite deliberate. We think we live in three-dimensional space. That is, we can specify the position of an object in a room by three numbers. They could be 5 feet from the north wall, 3 feet from the east wall, and 2 feet above floor level. Or on a large scale, they could be latitude, longitude, and height above sea level. On an even larger scale, we can specify the position of a star in the galaxy by three numbers: galactic latitude and longitude, and distance from the center of the galaxy. As well as the three numbers that specify position, we can add a fourth number that specifies time. Thus we can describe ourselves as living in a four-dimensional spacetime, where events are labeled by four numbers, 3 for the position of the event, and the fourth for its time. It was Einstein's stroke of genius to realize that spacetime isn't flat, but is curved and warped by the matter and energy in it. According to his general theory of relativity, objects like planets try to move on straight lines through spacetime, but because spacetime is curved, their paths appear bent, as if by a gravitational field. It is like if you placed a heavy weight to represent a star on a sheet of rubber. The weight will depress the sheet and cause it to curve near the star. If you now roll little ball bearings on the sheet to represent planets, they can orbit the star. We now have confirmation that spacetime is curved from the GPS navigation system, which is fitted to boats, airplanes, and some cars. This operates by comparing signals from several satellites. If one assumed spacetime was flat, one would calculate the wrong position. dimensions of space, and one of time, are all that we see. So why should we believe in extra dimensions that we can't observe? Are they just science fiction, or do they have detectable consequences? The reason we take the idea of extra dimensions seriously is that although Einstein's general theory of relativity agrees with all the observations we have made, the theory predicts its own downfall. Roger Penrose and I showed that it predicted that time had a beginning in the Big Bang and an end in black holes. At these places, the general theory of relativity would break down, so one could not use it to predict how the universe began, or what would happen to someone who fell in a black hole. The reason general relativity would break down in the Big Bang and black holes is that it does not take account of the small-scale behavior of matter. In normal situations, the warping of spacetime is very slight and is on comparatively long length scales. But at the beginning and end of time, spacetime will be scrunched up to a single point. To treat this, we need to combine general relativity, the theory of the very large, with quantum mechanics, the theory of the very small. This would create a TOE, or theory of everything, that would describe the universe from beginning to end. We have been searching for the theory of everything for the last 30 years, and we now think we have a candidate called M-theory. In fact, M-theory isn't a single theory, but rather a network of theories that all seem physically equivalent. It allows us to have several different descriptions of the universe, all of which predict the same observations and are useful in their own right. Remarkably enough, in many of the theories in the M-theory network, spacetime has more than the 4 dimensions we experience. Are these extra dimensions real? I must admit I have been reluctant to believe in extra dimensions. But the M-theory network fits together so beautifully, and has so many unexpected correspondences, that I feel to ignore it would be like claiming that God put fossils in the rocks to trick Darwin into believing in evolution. So how is it that spacetime appears 4-dimensional to us, but is 10 or 11-dimensional in M-theory? Why don't we observe another 6 or 7 dimensions? The conventional answer to this question, which was generally accepted until recently, was that the extra ELLRL flatted is like a human hair. If you look at from a distance, it looks like a 1-dimensional line. But if you look at it under a magnifying glass, you see the thickness, and that the hair is really three-dimensional. However, there has recently been a more radical suggestion that one or two of the extra dimensions may be much larger, or even infinite. Because these large extra dimensions have not been seen in particle accelerators, it is necessary to suppose that all particles of matter are confined to a brane or surface in spacetime, and are not free to propagate through the large extra dimensions. Light would also have to be confined to the brane, or we would already have detected large extra dimensions, and the same is true of the nuclear forces between particles. Gravity, on the other hand, is a universal force between all forms of energy or mass. It cannot be confined to the brane, but will permeate the entire space. Because gravity spreads out into the large extra dimensions, as well as along the brane, it ought to fall off more sharply with distance than the electric force, which is confined to the brane. Yet we know from observations of the orbits of the planets that the gravitational pull of the Sun goes down the further one is from the Sun, in the same way that electric forces fall off with distance. So if we do live on a brane, there has to be some reason why gravity doesn't spread far from the brane, but is confined to a neighborhood around it. One possibility is that the large extra dimensions end on a second shadow brane, not far from the brane on which we live. We would not see the shadow brane, because light could travel only along the branes, and not through the space between. However, we would feel the gravity of matter on the shadow brane. There could be shadow galaxies, shadow stars, and even shadow people who might wonder about the gravity they feel from matter on our brane. Instead of the extra dimensions ending on a second brane, another possibility is that they are infinite, but highly curved like a saddle. Lisa Randall and Raman Sundram showed that this kind of curvature would act rather like a second brane. The gravitational influence of an object on the brane would be confined to a small neighborhood of the brane, and would not spread out to infinity in the extra dimensions. But there is an important difference between this Randall-Sundram model and the shadow brane model. Bodies that move under the influence of gravity will produce gravitational waves, ripples of curvature that travel through spacetime at the speed of light. Like the electromagnetic waves of light, gravitational waves should carry energy, a prediction that has been confirmed by observations of the binary pulsar. If we indeed live on a Brane in a spacetime with extra dimensions, gravitational waves generated by the motion of bodies on the Brane would travel off into the other dimensions. They would be reflected back if there were a second shadow Brane, entrapped between the two Branes. On the other hand, if there was only a single Brane and the extra dimensions went on forever, like in the Randall-Sundrum model, gravitational waves could escape altogether and carry away energy from our Brane world. It is only the short gravitational waves that would escape from the Brane, and the only sources of significant amounts of short gravitational waves are likely to be black holes. A black hole on the Brane will extend to a black hole in the extra dimensions. If the black hole is small, it will be almost round. That is, it will reach about as far into the extra dimensions as its size on the Brane. On the other hand, a large black hole on the Brane will extend to a black pancake which is confined to a vicinity of the Brane, and which is much less thick in the extra dimensions than it is wide on the Brane. Some time ago, I discovered that black holes won't be completely black. They will emit particles and radiation of all kinds, as if they were hot bodies. The particles and radiation, like light, would be emitted along the Brane, because matter and electric forces would be confined to the Brane. However, black holes also emit gravitational waves. These would not be confined to the Brane, but would travel in the extra dimension as well. If the black hole was large and pancake-like, the gravitational waves would stay near the Brane. This would mean that the black hole would lose energy and mass, at the rate one would expect for a black hole in four-dimensional spacetime. The black hole would therefore slowly evaporate and shrink in size until it became small enough that the gravitational waves it radiated could begin to escape freely into the extra dimensions. To someone on the Brane, the black hole would appear to be emitting dark radiation, radiation that cannot be observed directly on the Brane, but whose existence can be inferred from the fact that the black hole was losing mass. It would mean that the final burst of radiation from an evaporating black hole would appear less powerful than it actually was. This could be why we have not observed bursts of gamma rays that can be ascribed to dying black holes, though the other explanation would be that there aren't many black holes with mass low enough to evaporate in the age of the universe so far. That would be a pity, because if a low-mass black hole were discovered, I would get a Nobel Prize. So how could a Brane world have originated? In my opinion, an attractive explanation of the origin of a Brane world would be that it was spontaneously created as a fluctuation of the vacuum. The creation of a Brane would be a bit like the formation of bubbles of steam in boiling water. Liquid water consists of billions and billions of H2O molecules, packed together with couplings between nearest neighbors. As the water is heated up, the molecules move faster and bounce off each other. Occasionally, these collisions will give molecules such high velocities that a group of them will break free of their bonds and form a little bubble of steam, surrounded by water. Most small bubbles of steam will collapse to liquid again, but a few will grow to a certain critical size, beyond which the bubbles are almost certain to continue to grow. It is these large expanding bubbles that one observes when water boils. The behavior of Brane worlds would be similar. Fluctuations in the vacuum would cause Brane worlds to appear from nothing as bubbles. The Brane would form the surface of the bubble, and the interior would be the higher dimensional space. Very small bubbles would tend to collapse again to nothing, but a bubble that grew by quantum fluctuations beyond a certain critical size would be likely to keep on growing. People, such as us, living on the Brane, the surface of the bubble, would think the universe was expanding. It would be like painting galaxies on the surface of a balloon and blowing it up. As the Brane expanded, the volume of the higher dimensional space inside would increase. Eventually there would be an enormous bubble, surrounded by the Brane on which we live. Matter on the Brane, the surface of the bubble, will determine the gravitational fields in the interior of the bubble. Equally, the gravitational fields in the interior will determine the matter on the Brane. It is like a hologram. A hologram is an image of a three-dimensional object that is encoded on a two-dimensional surface. I know all about holograms, having been one myself, along with Newton and Einstein, on an episode of Star Trek. In a similar way, what we think of as four-dimensional spacetime may be just a hologram for what is happening in the five-dimensional interior of the bubble. We take it as obvious that we live in a world of three space dimensions and one time dimension. But maybe we are just shadows cast by a flickering fire on the wall of the cave in which we have our existence. Let's hope that any monsters we encounter are also shadows. Brain world models are a hot topic of research. They are highly speculative, but they offer new kinds of behavior which can be tested by observation. They could explain why gravity seems to be so weak. Gravity might be quite strong in the fundamental theory, but the spreading of the gravitational force in the extra dimensions would mean it would be weak at large distances on the brane on which we live. If gravity is stronger in the extra dimensions, it would make it much easier to form little black holes in collisions of high-energy particles. It might be possible in the LHC, the Large Hadron Collider, that is based in Geneva. A tiny black hole wouldn't gobble up the Earth, as newspaper scare stories would have one believe. Instead, the black hole would disappear in a puff of Hawking radiation, and I would get a Nobel Prize. So onward the LHC. We may discover a brand new world. Thank you very much, and before I go I would like to make a shameless plug for the latest book in my series for kids. Out on the 29th of August it is called George and the Big Bang.